Hello, and welcome to Summarize Science. You've probably heard that AI has gotten exponentially better, but one study claimed it's become 22,000 times more efficient in training since 2012. That's an incredible number, but a group of researchers wanted to know where that massive gain actually came from. The common assumption is that progress comes from a series of small, steady improvements that add up over time. But is that really the case, or is the story more complicated? To find out, they first tested many of the individual innovations that have been developed over the years. As you can see in this chart, most of these well-known advancements actually provided very small benefits, many offering less than a 2x boost on their own. This doesn't come close to explaining that huge 22,000x figure. The real answer, they discovered, lies in what are called scale-dependent improvements. This graph compares the older AI architecture, known as LSTM, to the modern transformer that powers models like ChatGPT. At small scales, the transformer is only about 6 times more efficient. But as you throw more and more computing power at it, its advantage grows enormously, becoming 26 times more efficient at a larger scale. This brings us to the paper's main finding, summarized in this amazing chart. It shows that a staggering 91% of all algorithmic progress can be explained by just two major, scale-dependent changes. The first, shown in orange, is that foundational switch from the old LSTM architecture to the much more scalable transformer. The second major gain, shown in red, came from a better understanding of how to scale models, known as chinchilla rebalancing. The key is that you only see these massive gains when using enormous amounts of compute, like the frontier models from major AI labs do. At smaller, more accessible levels of compute, the total improvement is only about 155 times, not 22,000. This leads to another wild conclusion. How you measure AI progress is completely dependent on your point of reference. If you compare modern AI to the old LSTMs, progress looks like an unstoppable exponential curve. But if you measure it against a basic transformer, the rate of new algorithmic gains looks almost flat. So, let's recap the important points. First, AI's massive efficiency gains are not from a steady stream of small tweaks, but from a couple of huge, architectural shifts. Second, these breakthroughs are scale-dependent, meaning their incredible benefits are only unlocked with massive computing power. This has profound implications for the future. It suggests that future progress in AI might be fundamentally tied to our ability to keep scaling up compute. This also means that large players with huge data centers benefit far more from these innovations, and that the next big breakthrough might be hard to spot because it may seem unimpressive at a small scale.